And now, to introduce our opening session Ignite speakers, I welcome back to the stage Marian Avery.
Welcome to the Ignite session. Yay! How many of you have never seen an Ignite session? Oh my goodness, you are in for a really wonderful treat. The Ignite session is an innovative kickoff that will inform, amaze, and inspire while entertaining you as well. You're in for just a delight. Our speakers have backgrounds in mathematics with impressive credentials, experiences, and accomplishments. Each speaker will give a 5-minute presentation using 20 PowerPoint slides that advance at a rate of 1 slide per 15 seconds. They're all as nervous as I am. They are amazing people. I have spoken with them. I only just met 2 of them officially tonight, but have communicated by email several times over the last year and a half or so. The others I've known for a while. They're just amazing people, and they're very varied, so I think you're really going to enjoy them. So I'm going to introduce each speaker before they come up, and when they finish, I'll come back and introduce the next speaker for you. Our first speaker is Michael Steele. Oh, and I forgot to tell you that I asked them for some unusual tidbits to introduce them with. So Michael Steele is an associate professor of mathematics education and chairperson of the Department of Curriculum and Instruction at the University of Wisconsin-Milwaukee. He is a former middle and high school mathematics and science teacher from Maryland. When he is not working with teachers, you are likely to find him in his garage brewing some of the finest beer in all of Wisconsin, or gallivanting around town in a tuxedo, moonlighting as a musician. Please welcome Michael Steele.
Hello, Philadelphia. Come on, show me some brotherly love. Hello, Philadelphia! Oh! It's great to be with you tonight, although I think my phone's malfunctioning. I've been trying to catch this Pikachu right here, and I just can't do it. So we'll save that for later. I want to talk to you a little bit tonight. As Marian mentioned, I started my career kind of not too far from here, down in Maryland. And so putting this talk together, I started to reflect on my journey over the past 22 years and what stayed the same and what's changed. I dug into my digital archives. I'm a digital hoarder, and found some of the things from the very beginning of my teaching career. I brought some of them tonight to share with you. So I really wanted to start by thinking about my teacher preparation. So when I went through my teacher preparation program, I had 2 6-credit courses in pedagogy, 10 weeks of student teaching, 1 visit from a supervisor, go forth and teach kids to multiply. That was it. That was the preparation I got. And now I think about what I do with my own teacher preparation students. They're out in the field for a year in 2 different classrooms, me visiting, supervisor visiting, meaningful state and national assessments, thinking about student learning in really, really important ways. My classroom then, this is not an exact picture, but it was pretty darn close, I'll tell you. Those desks in rows with the unmovable desks and chairs with them, stuff on the walls, but nothing that changed. Let me show you where I teach right now with my methods course. We've got monitors, we can put up student work, we can talk about tasks that we find, we can talk about lesson plans, all interactive, all digitally wired, the entire internet at the touch of a button. I dug out my standards teaching 8th grade math in Maryland 22 years ago. That's it. That's the entire document right up there on the screen. I think about how that's different from what we have now. I tried to capture what we have now, and I could barely scratch the surface. We've got a K-12 spectrum that makes sense. We've got depth and detail at a grade level that I wish I'd had when I started teaching 8th grade math. It's absolutely amazing where we are now. My resources then, that was it. You're seeing a picture of it on the screen. That teacher's edition, and good luck. A lot of making stuff up as I went along. Today, I am so jealous of the work that the teachers that I work with do, is they've got all these resources, they've got their text, but they've got the math teacher blogosphere, they've got illuminations, they've got 3-act tasks, they have the entire world at their fingertips. They can say, this is what I'm teaching, and come up in an instant with 20 good ideas. What did pedagogy look like back then? Closed doors, right? Teach with your own style, get good test results, borrow worksheets, but don't you dare talk about your planning or teaching. So what does it look like now? I'm not sure we've gotten past that stage. Have we really gotten past those closed doors, that teaching style, and only sharing worksheets with one another? Have we really started to dig in what effective mathematics teaching is? Effective teaching is not a matter of style. I think we need to get rid of this misconception, and we need to start tonight. We know things about what effective teaching and learning looks like. We know about NCTM's Principles to Actions, 8 effective mathematics teaching practices. Come see me Wednesday, we'll talk about them. But this is a research-based consensus on what constitutes effective mathematics teaching. We know that this is what works. We have video of teachers using these practices. We have a consistent set of math standards, relatively speaking, and nearly infinite capacity for us to connect with one another and talk about our teaching. So now is the time for each and every one of you to take action. This is what I'm asking you to do tonight. This is what I'm going to ask you to do when you come and see me on Wednesday. It's time to start challenging these myths. I want you to be a model in your school. I want you to promote meaningful tasks that promote problem solving. I want you to get your kids talking to one another and talking to you. And I want you to empower your students as people who are capable of doing mathematics. I want you to open those closed doors and instigate, and I chose that word carefully, meaningful conversations with your colleagues about mathematics. What it is, why we care about it, and why kids should learn it. I want to settle the style argument. It's not we teach in the styles that we want to. Challenge that conventional wisdom. There are things that work and don't work. I want you to model it. I want you to engage your colleagues in it, and I want you to evangelize with your community around it. And that connects to this. Show the world the good work that you're doing. Videotape your teaching, share your tasks, but share your plans and your questions and your student work, and invite the parents and the community members that come into your classroom to ask you questions about why you do what you do. I want you to go out there and teach, I want you to study your practice, and I want you to share it far and wide. Thank you.
Chika Akua is from Atlanta, Georgia, and is the governor of the Teacher Transformation Institute, which provides culturally relevant professional development with effective instructional strategies to increase student achievement. He is a former Teacher of the Year, author of 10 books, and producer of 10 educational DVDs. And last Monday, he successfully defended his dissertation.
Everybody say, let's get it.
Let's get it.
All right, my name is Chika Akua, and I'm going to be talking about mathematical mastery from ancient Africa to urban America. I want to bring you greetings from the Teacher Transformation Institute, where we use standards-based, research-driven, and culturally relevant instructional strategies to increase student achievement. Now, as we get into this concept of mathematical mastery coming out of ancient Africa, Dr. Samori Kamara asks a question of us, and the question is simple. Have you ever been on social media and somebody tagged you in a picture, you clicked on it, only to find out that you weren't in the picture? Let me see a show of hands. That's what's going on in our classrooms today. And I want to tell you, what is the origin of mathematics? Do our children see themselves as producers of mathematical mastery? And so whether we're talking about going all the way back over 20,000 years to the discovery of the Ishango bone, which is a tool that was discovered in the Democratic Republic of the Congo, or whether we're going back to the Am's Mathematics Papyrus, which is the oldest mathematics textbook coming out of the Nile Valley of Africa, dealing with algebra, trigonometry, sine, cosine, tangent, cotangent, square root, area, circumference, and volume, and so much more. Or whether we're talking about the African father of medicine and mathematics, Imhotep, who was a multidisciplinary genius who introduced the world through his writings and through his research. These are resources that our children have no idea about, and they don't see themselves in the picture of mathematical mastery. I travel all over the world doing primary research, pulling together the pieces of this puzzle to show our children a picture of themselves that they oftentimes don't find in today's public schools. But today and tomorrow in my presentation, we're going to be dispelling the myths. Myths like the Great Pyramids were built by aliens. Come on, how many of y'all have heard that before, right? Okay. Or that it was built through slave labor. No, we have the documents to demonstrate who worked on it. We can talk about the fact that they were covered in polished white limestone with a capstone made of pure gold. What kind of educational system did these Africans, these ancient Africans, have to produce that kind of meticulous mathematical mastery? Whether we go back to the Am's Mathematics Papyrus and problem number 56, where we see these Africans working on how to determine and discover the slope of a pyramid. There's all sorts of different primary research data. We can also look at the majesty of the Moors and the African influence in early Europe and the way that these Africans lifted Europe out of the Dark Ages with their science, technology, engineering, and mathematical mastery. And so as we look at these different things, then we can go to West Africa and look at the University of Sankore at Timbuktu, where scholars from all over the world came. Now, when I was growing up, we had a saying, man, I'll knock you all the way to Timbuktu. I didn't know that was a place, much less one of the great learning centers of the world, where African scholars and scholars from all over Africa and all over Europe and all over Asia came to study at the feet of master teachers. And there are thousands, hundreds of thousands of these manuscripts that are still in existence. And then Dr. Runoko Rashidi, who talks about global African presence, demonstrates how through migration patterns around the globe, these Africans took their knowledge and their expertise everywhere that they traveled and influenced culture all over the world. Again, this is a picture of the possibilities that many of our children don't get these days. They don't see their own personal cultural connection with mathematical mastery. And we as their teachers must be able to show them and to demonstrate that it belongs to them. For the first time in the history of the United States of America, over 50% of the public school population will be children of color. Are we prepared to engage them on their level? You see, we can ask questions. Was there a time when African people led the world in mathematical mastery, scientific innovation, literary production, and wealth creation? We can examine these questions, but are we prepared to engage the children on their level when in fact they now are the ones that are the majority of the public school population? And we understand that when we can relate to them in this way, they will be much more receptive to what we have to teach. As I mentioned, I traveled all over the world in search of these and other gems that I'm prepared to share with you tomorrow. And I look forward to sharing those with you tomorrow. And I believe, as educators, we can change the world if we are first willing to change ourselves. My name is Chika Akua, that's my story, and I'm sticking with it. Thank you.
Rosemary Sebeck is Professor of Mathematics Education and Department Head at the Pennsylvania State University here in Pennsylvania. Rose loves roller coasters so much that she has a season pass to Kentucky Kingdom, and as she said, she has been a card-carrying member ever since the park reopened, which she said was in 2014, but she's been on roller coasters way before that. Competing in the United States and Canada, Rose's high school band won more than 200 first-place trophies during her senior year. She played the tenor sax and the bassoon, and she says, but not at the same time. Please welcome Rose.
Good afternoon, everyone. I know you're here for the same reason I am, and that's because you're passionate about teaching mathematics. I'm passionate about teaching kids to be modelers, and what do I mean by that? Mathematical modeling is a process. It's a process that uses math. It's not just math, it's also the real world. So we've got to be real about what mathematical modeling is and look at problems like this. This problem is messy, it's long, it's hard, it takes up a long time and a lot of pages. You can check it out on that URL if you want to. You're going to find out when you look there, it's about building a model, not just doing calculations, because math modeling is for people who want to solve real problems about what they're doing. That is great stuff. It is the kind of stuff that makes kids realize why STEM, STEAM, or STREAM is important. It helps them understand what it means to move from high school into college, into careers, or into citizenship. It's also the kind of stuff that happens when we want motivation for why we're doing what we're doing in our classes. But why are we not doing enough of it? We're probably not doing enough of it because there's not enough time. It takes time to do these things, let alone prepare them. We have a curriculum we have to worry about. There might be some things about the standards that are unclear. We have to worry about resources. We're interrupted with other things, and we have some expectations about math. What about those expectations? Most kids think that what they should do when they're solving a problem is they should start where they are, and they should go to a right answer, like that. There's no fuss, there's no muss, you just go there directly. That's not necessarily what we mean when we're talking about modeling. Think of it this way. Instead of worrying about a right answer, we're talking about having a useful model. You might start there, but the path you use to get there might go around. There might be some stop starts. There's some messiness to that. But you still get to what a useful model might be at the end. If I'm going to think about that, I might think about making mistakes, hopefully in the right direction. And students, when they're working as modelers, have an opportunity to enjoy what it means to understand the real world. They're going to talk with each other. They're going to come to some conclusions, and they're going to have those moments of joy when they get that idea about what works right and it's going to happen for them and work all the time. Our job then is to build a generation of modelers. That means that teaching modeling is not the same thing as doing modeling in front of kids. It's not going to be the same thing as watching them model. It's not just giving them an assignment that's modeling. You know that great problem at the beginning? That's not enough just to give them that. We have to have some other ways to do it and help it on a daily basis. So think about that modeling process with me. It involves having some revision. It's going to be messy. It's going to take assumptions, and we're going to have to worry about making some genuine choices, and my goodness, there's a lot to doing all that. So where do we start? You might have a favorite modeling diagram. You might like the one in Common Core. You might take the one from the annual perspectives in mathematics education. Perhaps the one you prefer is the one from the game document. You might find some in research, or you might find one from one of our sister organizations in mathematics. I like that one because, look, it spends all those red dots talking about what it is to research and brainstorm what happens in the real world and connect that with mathematics. But hammer this thing apart. When you do that, you find out this whole big process is something that's very large to take on, and maybe we need to break it into some pieces. So would you break it into pieces with me and think about what we can do on a daily basis with our kids so that the tasks we use every day help them become better modelers as they move on? I'm thinking about the kinds of things we do and discuss every day. Can we think in every one of those parts? Where is it that we're going to do something about mathematical modeling? Here's an example. Jane buys 6 cans of soda for $1.74. I have no idea where she shops, but it's a great deal. Think about it. What happens if you can buy 10 cans? Not the 1 or the 24. Those are too easy. When we think about that particular question, we might find it in proportional reasoning. We might find it in a linear equations chapter. Check it out. We can come up with a line. We find the graph that looks beautiful. We get the point. We think we're done. At that moment is when we can introduce more modeling into our schools and say, wait a second. Look at that line. Is it really a good graph? Where does it fall short? What are the things we want to do? Particularly what happens if we look at that thing and we want to talk about selling not 1, not 24, but 10 cans of soda. And what would that thing cost? If you think about the way we have soda, the cans are whole. We don't get a third of a can. In that case, we have to think about and introduce the idea of what a domain might be that consists of all the natural numbers. In that case, we're still going to have that little green point. Do you see it there? That's still the 10. I think it's still $2.90. Looks good, but we've introduced something new. We've given kids a way of thinking about math in the real world. How about this one? We really buy soda in those 6-packs. They're not going to let you throw 2 cans of soda on the shelf and walk out with only 10 of them. They're going to worry about what that is, and they're going to charge you $3.48 for that privilege. When we introduce those things, we're going to be doing things that help our students connect the math they're doing, the things we're asking them to learn, and put that together in a different perspective with the things that they need to do in their everyday life and in their careers and in thinking about math in the future. We need some tools for doing this. I want to share with you on Wednesday some tools for doing that. There are 3 kinds of tools I have in mind. The first is let's take this big messy process, divide it into little pieces, and come up with those things that we can insert in our lessons on a regular basis that will help kids become better modelers. We'll have criteria for what modeling tasks are, and we're going to think about running from a math problem to a modeling problem, including applications. I want you to come with me and embrace the modeling moments here in Philadelphia and in your class. And there's one more thing. I want you to know that your students recognize that you are a model teacher. Thank you for being here.
Tom Reardon spent 35 years at Fitch High School in the same room for his entire career, and 36 years at Youngstown State University, Youngstown, Ohio, currently teaching a math methods course. Tom owned and operated a dry cleaners his first 10 years of teaching. Please welcome Tom Reardon.
Before I get started, I have to tell you, I can't talk that fast. I didn't know that was one of the requirements. Is that one of the requirements? So, go ahead and start? Okay. It's better to know how to learn than to just know. Anybody know who said that originally? Maybe if it would have rhymed, okay? We're going to look at innovative ways to teach reflections, dilations, translations, and rotations. Some tools that we've already done are paper folding, mirrors, compass and straight edge, grids, patty paper, and dynamic geometry software. Come on, speed up. When used correctly, these have been good, hands-on, tactile ways to have students learn. They have served us well. However, there is a lot of time spent preparing lessons, even with dynamic geometry software. So what if you could create your lesson so that prep time is minimal and the students spend almost all their time playing, investigating, exploring, and discovering the math concepts? Now this is a certainty. Appropriate technology use creates a better, richer learning environment. It also allows the students to do or investigate mathematics that he or she is unable to do otherwise. More efficient, understand quicker, more deeply. So let's investigate the relationship between the ratio of areas of dilated triangles. Students are able to explore many pairs of triangles quickly, make a conjecture, and then verbalize it. Then easily test the hypothesis using the built-in tools that we have supplied. And conclude that the ratio of the areas is the square of the scale factor. This is exactly how I want my students to learn. I would want them to draw conclusions, quickly see several possibilities, generalize if possible, and prove. Imagine doing these types of activities by hand. I took this photo at the Taft School in Connecticut when I taught a summer workshop, never thinking I would use it today. We've created several templates so that students can quickly set up the activity and then spend their valuable time exploring. Here we are investigating the relationship among coordinates when reflecting a triangle about different lines. Here we can look for patterns, change the triangles, and notice we can reflect about really any linear equation. Next, investigate reflecting about the y-axis, look for patterns, again change the triangles. My favorite line to explore is the line y equals the opposite of x, because it is not normally done and it has very interesting results. And now we can do it with technology. The goal is for students to generalize their findings and be able to verbally explain the results and symbolically represent them as shown here. That's our goal. How many of you have taught rotations? It's a tough one for students. Here I'm rotating triangle ABC about point P through an angle of 135 degrees. And when I ask my students, how would you do this by hand? They all say they have no idea. It's magic. So we put in some tools to help students visualize better. See the eyebrow button at the bottom? Tap it 3 times and observe. First you see the arcs, then the concentric circles, and then the arcs traveling along those concentric circles. And after seeing this, students tell me, give me a compass and a protractor, I can do this. And this is exactly what we want to happen. Students create their own learning and their understanding, not just tell them what needs to be done. Most teachers, unfortunately, teach rotations of 90 degrees only. That's the only angle, with a grid, and just tell the students what to do to the coordinates. Now the students are able to discover what those patterns are, as shown here. Using this technology, students and teachers spend most of the time exploring and learning. They find out how to do these on their own without being told. And they're encouraged to discover the definitions and properties. They're expected to look for patterns, make conjectures, test them, and consider counterexamples. Now compass and straight edge constructions will make more sense. Students will better see how to apply these things to solve problems. And my final quote, mathematics is the garment that we continuously alter with our students, and technology should be seamlessly interwoven throughout its fabric. Oh, that was me, okay. Well, thank you for coming and have a good time.
Sarah Delano Moore is an educational consultant from Kent, Ohio. Sarah is a cat person. She drives about 3,000 miles per year and received her master's degree in general linguistics and comparative philology. I had to look that up. How many of you know what philology is? It is the study of literary texts and of written records, the establishment of their authenticity and their original form, and the determination of their meaning, especially historically and comparatively. Oh, that was pretty neat. Sarah is a knitter and a quilter. She having learned to knit when she was a child and learning to quilt as an adult. And Sarah told me that these hobbies help to keep her sane. Please welcome Sarah.
Kipling talks history. We're here to talk math tonight. But this whole idea of if we teach in the form of story, children remember what we have to say. Things won't be forgotten. Our job, particularly as teachers of young children, is to preserve and protect the enthusiasm they have for mathematics. They come loving it. And by the time they get to middle school, not so much. We want to establish a strong foundation. We want to keep them moving. So we use all the different representations that we have. What I want to think a few minutes about tonight is this idea that if we bring together the physical representation with the contextual representation, we end up with narrative. We end up with mathematics as story. And the story is the math. This isn't read a story, then go do math. This is that the story is the math. It's where it's grounded. And that means that we have to think about, as we work, the elements of story. We need a plot. What's going to happen here? We have conflict and resolution. We have characters. We have settings. We have props. Props are critical because they're what make the stories mathematical stories, not just a tale we tell. No naked numbers. They really don't make sense, so let's just skip them. It really is one of the most powerful things I think we can think about. Our storylines with primary children are really about adding and subtracting. So if you know table 1, these are the 4 rows, and they form the basic plot lines of the mathematical stories that we tell. The conflicts in the story are the questions. What are we trying to figure out? Do we want to know what the difference is? Do we want to know a total? The resolution to the story is the solution to the problem. What's our answer? We're still doing our math, but we're doing it in the context of story. And our mathematical props, whether formal manipulatives or more informal tools, are things that we can use to feature and highlight the mathematics. So let me tell you a couple of quick stories about my friend Norma Jean. She's a kangaroo, she likes to jump. She collects toy cars. And she had 5, and then when she got some more for her birthday, now she has 8. And the question is, what's the storyline? What's the narrative for figuring out how many she got for her birthday? In a classroom, we'd have a number line in the front of the room and kids hopping along. You get animated Norma Jean instead. Had 5. How many more is it going to take to be 8? How many hops does that require to move from 5 where I started to 8 where I am? When children do this, and they are the story, and the story is the mathematics, it brings great power to what they remember and what they learn. Is the number line always the right prop? No. Is jumping along the number line or a motion at all always the right strategy? No. Depends on the problem. So if we think about Norma Jean and her friend Ted in a different problem, now we're looking at the books that they have. Norma Jean has 4, Ted has 9. I don't need a prop that will let me show motion here. But seeing those two values is a really big deal in this work. So I want to choose a model that will let me do that. In this case, I'm going to pick Cuisenaire rods, so my purple rod is Norma Jean's 4, my blue rod is Ted's 9, and my mathematical question, my resolution to the story, what fills in the gap? What's the piece that comes in the middle and shows us that in fact Ted has 5 more books? It's that yellow rod. Could I use the number line as my prop? Sure. That would work, but it's going to look different than the number line did last time because I don't need to move here. Nothing came, nothing left. I'm worried about how far apart Norma Jean and Ted are. So in class, we've got 3 kids now. We've got Norma Jean, we've got Ted, we've got a counter to help us think about how that works. What that means is that we're using these tools, we're using these manipulatives as props. We're thinking about what's the mathematics that they show, how does it bring that to life, so that the story is the math for the kids. The storyteller's deep inside all of us as grown-ups. It's not so deep inside the kids. So if we can dig it out of ourselves and use that as a way of teaching the math, then what Kipling started us with becomes true. The children remember the math and they never forget it because it is the story. Thank you.
Jimmy Davis Jr. was a high school mathematics teacher before returning to school to earn his engineering degree and currently serves as president of STEM Florida Incorporated. I happen to know that he has more than 2 degrees, by the way. Jimmy is a backyard gardener with an orchard of more than 100 different varieties of figs. Also in his garden are blackberries, blueberries, lemons, oranges, satsumas, grapes, guava, kiwi, mulberries, pawpaw, peaches, pears, persimmons, pineapples, plums, pomegranates, raspberries, and strawberries. Now, I don't know about any of you, but that makes me pretty hungry for a fruit salad. According to the Morehouse College Media Guide, Jimmy is the all-time record holder for career passing yards and most touchdown passes in a game, a season, and a career. Please welcome Jimmy.
Good evening.
Good evening.
Good evening. Good evening. Hey, so I'm an engineer. I never taught high school math. No, didn't tell you. I'm a practicing engineer, and I'm here. Yes, I'm here because a little bit more a year ago I met Marian at a conference. And it was the last time I was in Philadelphia, and I was in Lancaster, PA, and I spoke, and I wasn't sure if I was in the right place because I was talking to a whole bunch of teachers, and I'm an engineer. So about this math conference, Pennsylvania has significance because these are the first 3 African Americans to earn PhDs in math, and they were all at UPenn, and they were all, their advisors were all Robert Klein. Why is that important? This is how I learned mathematics. A shopping cart, grocery cart with my mother. She made me to add up everything in that cart and have tax and be within 5 cents every single time I went. So you as teachers, think about how you relate to your students and give them things that are practical, that makes the math, the story, something that they will remember forever, because that's when my love of mathematics started. And then I went to college at Morehouse College, and I started doing mathematics like this. Vedic mathematics comes from the Vedas. It's ancient Hindu text. So I know you know this math, right? 25 squared, 625. You see patterns. You recognize those patterns. This was my very first research project in college, and I just fell in love all over again with math. Math is my first wife. And what you'll learn and what you'll hear tomorrow is that was a very good wife that I had. 97 times 93. These are two numbers that are close to what that is a power of 10. 100. How far away is 97 from 100? 3 less. 93 is 7 less. These are the techniques that we learned, that I learned in college. So imagine if we can teach students a different way. You learn it one way, you unlearn it, and then you have to relearn. If I leave with anything tomorrow morning, it is to learn, unlearn, and relearn. That is the most powerful thing that we can do. And just to show you some reference, I majored in math, physics, and electrical engineering when I was in college, all at Morehouse College. And here I stand. So I was a lover of math, and I recognized some things, is that the stories that I learned very early, they carried me through. So playing football. Hey man, you have to move a little bit quicker. We did some math problems where we had to learn the trajectory of throwing a football, right? At what rate, at what height, gives you what distance. We teach the rates. So now I work at the Miter Corporation. All of my tests are open book, any book. I can call any friend, invite any friend. I can schedule a technical interchange meeting. I can do whatever I want to get the problem done. And yet our students do what? Sit in the classroom, closed book. You can't do much other than use the brain that you have. That's not the way we do it in the real world. That's not the way we do it at the Miter Corporation, which is where I work now. So one of my tests was out at White Sands Missile Range. We were there with several subject matter experts. We could do whatever we want. This was my classroom. This was my playground. This is where I took all of my algorithms, the pedagogy, and learned. And then 2 years later, I went out 50 nautical miles off the coast of Hawaii, collected 10 terabytes of data to translate into, 20 slides with 15 seconds for each slide. And I do that work to live, and this is the work I do to have fun. These are trends in 8th grade math students. My son is an 8th grade math student. I need these trends to change. I need them to get better. And one of the ways for those to get better is to do hands-on, out-of-school, after-school projects. And much of what we talk about in terms of storytelling, in terms of the University of Timbuktu, in terms of the places that we live and we grow, it requires some changes. And my talk tomorrow is about building that STEMpire. It started from the cart, it went out to the fields of White Sands Missile Range, to the boats. And the number one thing I want to talk about is self-apprehension. You have to grab yourself, shake yourself, learn, unlearn, and relearn. And these are the quotes that I kind of carry around and tell all the time, because if you don't, as teachers, challenge yourself, challenge your students, not just with the algorithms, not just with the pedagogy, not just with the curriculum, not with just the 50 minutes, then what will we all be? And who will sit here in the future? I think that's my last slide. Thank you very much, and I hope to see you tomorrow.
Well, we all know that Matt Larson is our current NCTM president. When I asked him to give me some little tidbit that I could share, he sent this to me. Matt says people often ask him if he has lived in Nebraska his whole life. He says that nearly everyone that lives there has. Few people move there on purpose. But that the real reason he lives in Nebraska is that his wife is in the Witness Protection Program. Oh, now, when I read that, Matt is a jokester. He has a serious side, but he's a jokester. I, on the other hand, am very straight-laced, gullible, very serious. So I'm thinking, oh, this is kind of funny. And I laughed and I went, oh, wait a minute, maybe he's just telling me that and I need to check. So I had to email Matt back, and he said, yeah, I'm joking, Marian. I said, okay. So I shared this with my husband. He had a good laugh too. So anyway, please welcome Matt again.
Imagine, if you will, that contentious standing room only parent meeting on your new math program. I was in just such a room a year ago. The meeting ended, and I left feeling beat up and depressed. And I asked myself a simple question: why? Everybody in the room wanted exactly the same thing. We wanted our students to be successful in mathematics. And the changes we had made in our program were producing the best scores ever on the state test. Part of the problem is that we live and work today in the shadow of the stereotypes of instruction first established in 18th century America. The first American math textbook established the process of teaching mathematics as state a rule, give an example, practice the rule. In 1821, the inductive method was offered. Here, kids were supposed to work through a series of examples using concrete materials to discover and understand the rules. So within the first 50 years of this country's founding, the great debate was established. Should kids learn rules, facts, and procedures, or concepts of understanding? And how should that math be taught? The history of math education in the United States is a 200-year pendulum swing between these goals. In the 50s and 60s, we tried new math. The goal was for kids to understand the structure of mathematics and develop the habits of mind of mathematicians. We all know new math didn't stick, and the country went back to the basics. In 1989, NCTM began the standards-based reform effort. By the late 90s, those standards were under attack. The criticisms then were the same as they are now with respect to the Common Core. Parents expected teachers to tell, educators expected kids to think. In 2010, we get the Common Core standards. We think maybe the pendulum swing will finally end. Those initially well-received standards are now under attack from both the right and the left. Why? Why all the controversy? Usually it's nothing but misinformation. Some people think the Common Core is a conspiracy. Okay? Some people confuse standards with assessment. They confuse it with curriculum. They confuse it with instruction. And now all this misinformation spreads virally through social media. Some of the famous posts that went viral include using the number line to understand subtraction, or the 10 frame to develop number sense. But in both cases, the objectors confused an instructional strategy with a mathematical standard. Our challenge is that teaching mathematics is a cultural activity. Most adults in America have experienced 2,000 hours of math instruction. This creates an expectation in their head about what effective teaching and learning is supposed to look like. But we didn't all grow up watching a doctor at work for 180 days for 13 straight years. So we trust the professional expertise of our doctor. And when she treats us with the most recent and effective, protocol, we don't push back and say, "Oh no, use leeches, please." Well, so now this slide is crap because you called it. We know the research, it's in principles to actions, and some of those research-informed instructional strategies are purposeful questions. Build procedural fluency from a foundation of conceptual understanding. And as Robert said, support productive struggle in learning mathematics. But we have to be careful how we describe these strategies to parents. Every parent understands productive struggle as long as it's applied to music or athletics. They all think their kid will grow up and be the next LeBron James or Taylor Swift through hard work, practice, coaching, corrective feedback, right? We have to communicate learning mathematics is no different. But call it effort, not struggle. We need to communicate to people what mathematics literacy means in the 21st century. It means our kids need to learn how, why, and when. We need to seek equilibrium in mathematics instruction and learning. We need to stand up for standards in common. Fractions and decimals are not different in Maine than they are in California. There is no such thing as new math. There is no such thing as Common Core math. But there are new instructional strategies. Once the goal was just to know how to do something. Now the goal is to know why. So we use visual representation. We use meaningful algorithms so kids understand the mathematics. Know how, know why, and know when. There's no reason this should be controversial. None at all. We need to point out to our critics that math achievement, particularly at the K-8 level, is up. Okay, it is higher for our students today than it was when their parents were in school. Why would we go back to a period of instruction that led to lower achievement? My call to action for you is to make sure our students learn how, why, and when. We owe it to them. We owe it to ourselves. We owe it to our country. Thank you.
speakers tonight. A terrific job. Let's give them another round of applause. I want to thank Marian for once again serving as program chair. A lot more work than anybody knows unless you've been a program chair. I want to thank you for being the MC tonight. Much appreciated. That officially concludes this evening's opening session. I want you to enjoy the evening, enjoy Philadelphia, enjoy the conference, and we will see you all in April in San Antonio. Have a great evening. Thank you very much.